Let me revisit assignment 7 just for a moment. I discussed it in the last lecture, and in problem 3 part 6 I had asked you to consider the case when the capacity is reduced. So, R25 had a flow of 15 units, okay, in the optimal solution, right, and U25 was also 15 is given to be, right. Suppose I want to make U25 go down to 10 units. Text also I had discussed the situation when the capacities go up, but in this case now for a basic arc, if the capacity goes down, then all that is happening is, see, you have a node 2 here and node 5. So, you were sending 15 units of flow here from 2 to 5, because U to 5 is 15, but we also had 15 units of flow from 2 to 5. So, now if you want to reduce the capacity here to 10, that means you have to find a path through which you can send 5 units, because you have to cut, you are not able to send more than 10 units here, but the BIs demanded that you have 15 units of flow here. So, you have to now divert 15 units of flow from 2 to 5. So, that is all. When the capacity went up, then you were trying to send, so you said that you will send extra amount from this node to this, and then you will try to send the same amount, the increased amount from here to here. So, now you just reverse. So, that is it. So, you use exam, that is what I said in the assignment when I was discussing the assignment, that you have the tools. So, the only thing you have to now consider is that you need to send the reduced amount from 2 to 5, and you do the same steps that for example, you will find first a path in the current tree from 2 to 5, and if you can, if it has some extra capacity, you will try to send some amount from along that path. If some arc gets blocked there, then you will use the dual simplex step. So, therefore, you can manage the thing. I just thought that maybe I will give you this hint, and then you can work it out on yourself. Okay. Now, so we were discussing the max flow problem, and let me just revise quickly the we had defined the problem. I had told you given you the dual also. So, we come back to now max flow problem. So, our formulation was maximize V subject to sigma x s t minus V equal to 0, then summation x I j summation j minus summation x k I, because you are talking about node I, summation over k is 0, and then minus summation x j t summation over j is equal to minus V. Or okay, since we are writing it on this side, let us make it this, that is what we are writing, plus V is 0. Okay. And then we had that x I 0 less than or equal to x I j less than or equal to u I j. Fine. So, the first constraint should actually read as sigma x s j, because s is your starting node. So, it should be x s j and summation over j. So, whichever nodes are connected to the starting node s, for all those you have these variables x s j minus V should be equal to 0. This is the first constraint. Then we wrote the dual to this problem, or whether you want to call this the dual, it is up to you. So, anyway, then the corresponding dual problem is minimized. So, you have only uij's here on this side. So, we said this will be minimization of uij wij, and then for the xij columns you have plus 1 and minus 1. So, subject to pi I minus pi j plus the I will not consider these as explicit constraints, right, only these ones. So, you have Vij, right, and since your xij's are non-negative, so you will minimization, this will be greater than or equal to 0, because xij now we are treating as greater than or equal to 0. So, these are my implicit constraints, and therefore, the corresponding dual constraints would be greater than or equal to 0, right, and there is no sign restriction on the V's, and So, so you will say that Vij's are greater than or equal to 0 for all ij, and your pi i's are free, unrestricted. Okay. So, this was the dual, and then I showed you that if you take a cut S S bar such that S belongs to capital S and T belongs to S bar, then the solution where pi I is 0 for I belonging to S and is equal to 1 for I belonging to S bar, right. So, which means that pi S will be 0 and pi T will be 1, right, and Vij is 1 for I belonging to S and j belonging to S bar, and 0 otherwise for all other cases, right. So, we showed you that we looked at it, we considered all possible cases of the dual constraints, and I showed you this is a dual feasible solution. So, therefore, and so that means the this is a cut, and I defined to you the cut set S S bar was collection of all I j belonging to A such that I belongs to S and j belongs to S bar. So, these were all arcs going from S to S bar, and so this is your cut set, right. And then we also defined the capacity of the cut. So, capacity of the cut S S bar is equal to Uij summation Uij I belonging to S and j belonging to S bar. So, all the arcs which are going from S to S bar and they are adding up their capacities gives me the capacity of the cut. So, this is a dual feasible solution, and you see that for any cut the value of the objective function, yeah. So, for the cut S S bar, dual objective function value is actually equal to summation Uij, which is the capacity of the cut, I belonging to S, j belonging to S bar, which is the capacity of the cut S bar, right. And by our this thing, see, it's a minimization problem, so I am calling it the dual, but by our tradition or whatever you call it, this was considered as the primal problem, but that does not matter. The important thing of the duality theorem is that the min objective function will be always greater than or equal to the max objective function. So, here you see that if this is the flow, so for any feasible flow you have the value V. So, then you immediately get that for any feasible flow V, right, and any cut S S bar, your V is less than or equal to capacity of S S bar. Now, as I said, we can look at a cut in so many ways. See, when because you have partitioned the node set and S is in one set, one part of the partition, and T is in the other partition, then you see all paths. So, here I have drawn this graph and you can look at it. So, what essentially another way to look at a cut is that all paths from S to T will have an arc in the cut set of any cut S S bar. So, because it just divides the network into two disjoint sets, therefore, any path. So, for example, here if you consider the cut, look at the cut S equal to 1, 2, 3, right, and S bar will be oh sorry, they should include, so okay, so S is, I am taking this as the cut. So then in that case it is S1, 2, 3, S1, 2, 3, and S bar will be 4, 6, 4, 5 and 6, 4, 5, 6 and T. So this is your S bar, right, and your cut set therefore is cut set S bar is all arcs from S to S bar, and that is, you see, 1, 4, then 3, 5 and 2, 6, right. These are all the 2, 6. And now you can just verify for yourself that the cut set is this, and any path from S to T will have one of these arcs in that path. Okay. So therefore, since the flow from S to T will be across all these paths from S to T, the total flow in the network cannot exceed the capacities of these 3 arcs, because whatever flow you want to send from S to T has to use arcs 1, 4, 3, 5 and 2, 6, right. So the total capacity when you add up of these 3 arcs, the flow cannot exceed this. So that is one way of looking at it, but since we have studied linear programming duality theory in detail, therefore one can also immediately use the duality theory and say that the flow will always be less than or equal to the capacity of any cut. And so by the duality theory, whenever you have a flow in the network and you have a cut such that the flow is equal to the capacity of that cut, then this cut will be the minimum cut, we will call by our nomenclature, and V will be the max flow, because we have proved this from the duality theory that if for a feasible pair the 2 objective function values are the same, then they must be optimal and the corresponding solutions are optimal. So we will continue developing on this. Okay. So this is your what we are trying to show here, and then yeah, now let me simply prove one simple result here. Net flow across a cut S bar. So okay, now since so for any feasible flow, I want to show you what will be the expression for net flow across a cut, right. And here what we do is, in this case, just add up these flow conservation equations. So I'll just write it out, add, because this is for each I, right, for each node there is a constraint. So this is for S, and then this is for I, and then this is for the node T. So just add the flow conservation constraints, add the flow conservation equations for all for I belonging to S only, right. So that means since S belongs to small s belongs to capital S, so this will be added, and here I will simply add these equations for corresponding to I in S. So which means that I will get the equation summation xij I belonging to S, and j of course varies over this, minus summation over j and I belonging to this is I belonging to S of x k I, and this is equal to V, right, because the first constraint has this number V here, which I write this way. So I am adding up this plus all other for all other I's for which belong to S. So part of them I will use, the remaining ones I will leave out. Okay. So this is the equation you get. Now, I have written J here. This is K. Okay. Now let's break up this summation, because J and K are varying over the whole node set. So let me write it up as right. So this will be summation xij, or okay, you want me to, I'll write the double summation. So, this is I belonging to S and I belonging to j belonging to, because remember j is varying over the whole node set. So, j belonging to S, right, and plus, because this summation I am breaking up. So, summation x I j double summation, again I belonging to S and j belonging to S bar, right, minus same thing here, summation double summation x k I, and here this is summation k belonging to S and I belonging to S, right, that is already there. Then this one I am decomposing. So, minus summation double summation k belonging to S bar and I belonging to S is equal to, oh sorry, okay, write x I j equal to V. See the equation when we are summing up over, when we are summing up the flow conservation equations for all nodes in S, then the equation should actually read as, now this here I am breaking up the summation over V as S and S bar, because S union S bar is V. So, therefore, the summation will read as summation over I belonging to S, then summation j belonging to S plus summation over I belonging to S and then j belonging to S bar. So, that takes care of the first set of summation. Then minus similarly k belonging to S and I belonging to S, then the second term is k belonging to S bar and I belonging to S. So, this all adds up to V, because we are adding up all the we are not adding up for the last node, the last equation is omitted. So, then I get this equation, and then of course, we further go on and analyze what I was computing the net flow, right. And then by mistake in further slides also I have been writing sigma double summation x k j, but actually it should continue to read as summation x k I. Okay. So, the summation is over k and I. So, now see here this and this cancels out, because this is summing up x I j when I and j both are in S, and similarly here also you are summing up all x I j's where k is in S and I is in S. So, these two cancel out, right, and so you are left with the expression, yeah, let me just subtract this here. So, we are looking at net flow across a cut, right. So, when this is this cancels out and you are left with summation I belonging to S, summation j belonging to S bar x I j minus summation, right, double summation k belonging to S bar and I belonging to S of x I j is equal to V. Why would I get k belonging to S bar and yes, I belonging to S, and okay. So, this is what this gives you, the flow from S to S bar, right, and this will give you the flow, right. So, the net flow in the right. So, what we are saying is, see here, maybe I can draw the diagram here. I need that expression. See what I am saying is, yeah, okay, this is S and this is S bar, and your small s belongs here and your t belongs here. So, you have arcs going like this, right, and then you have arcs going like this from here. So, when we talk about the net flow across a cut, what we mean is that, see, this much flow along the forward arcs is going from S to S bar, and some flow along the backward arcs, that means arcs going from S bar to S, there is some flow. So, the net flow would be adding up these forward flows minus the backward flows. This is what we mean, right. So, therefore, this is your net flow across the cut, fine. This is k belongs. So, actually the arc here I j, where I is in S bar and where k j, right, where k is in S bar and I is in S, right. So, you can immediately see from the figure that this is actually going from S bar to S, these arcs. So, you are adding up these and subtracting. So, therefore, this is the expression for. So, this is equal to net flow across the cut S S bar, and this is also equal to the flow which is in the network, because V is the total amount which is being sent from S, and since we are not violating these flow conservation equations, so whatever flow is sent from S will be reaching T. So the total flow in the network is V, but I have also shown you that the flow across a cut will always be, flow across any cut will always be V. Okay. So this will now be helpful to us. Okay. So maybe we can take up an example here. Just see. So take any cut here, and yeah. So now let me come to this example. So here the first number is the capacity, okay, and this is your flow in the. So I have shown you a network here where with the arc capacities and the flow that is there on the network. So if you look at, say for example, look at the cut S is simply this, and S bar will therefore be 1, 2, 3, 4, 5, 6 T, right? And so what is the net flow across this cut? Net flow across S bar. Remember, so we have to look at what are the forward arcs. So in this case there are no backward arcs, therefore the net flow is simply XS1 plus XS2, which is 8 units. This is the flow across the cut. Okay. Now, but if you look at, okay, let's choose some cut in which you have a backward arc. Yeah, okay. So if I choose, say for example, this cut, look at this cut, you have a backward arc here. So therefore here S will be small s, S1, and that's it. I'm just choosing this two, right? And then S bar will be 2, 3, 4, 5, 6 and T. This is a cut, and let us see what is the net flow across the cut. So here net flow, so add up the forward arcs. So what are the forward arcs from S to S bar? From S to S bar you have this, and you have 1, 3 and 1, 4. Yeah, just see clearly the forward arcs from this cut. So S is connecting to 2, and then 1 is connecting to 3 and 4, right? So the total flow is 4 plus 1, this thing, and 1, 4 is 3. So this is that okay? Have I written 3 and plus, right. And then minus the flow across 2, 1, right, because this is the arc going from S bar to S, but that is 0, so there is no flow. So therefore this is equal to 8 again, which is, so for you choose any cut, whatever the flow in the network, if your this thing is okay, if these numbers are okay, and this is another way to check whether your numbers are all right or not. So then the net flow across any cut must always be equal to the flow in the network. So this is what the situation is. And now let us look at, so I have already said the what would be the min cut max flow theorem, but let's write it out and we can prove it in a nice way, because you have this by now, I would say you have a strong background of the LPP theory. So let us now write down the max flow min cut theorem, prove it, and then we'll try to come up with an algorithm. Yeah, and then yes, so let us do that. And I already gave you the interpretation of the primal dual algorithm. I showed you that a primal dual algorithm will actually reduce to finding an augmenting path from S to T and then trying to augment the flow. So this is what we are going to now formalize after I prove the min cost flow theorem. I'll formalize the algorithm of building up the max flow by selecting, by finding augmenting paths at each iteration. So let's work out those details. Okay, max flow min cut theorem. Okay, this says that if, so we have a network N where your source and sink nodes are specified, V is the node set, A is the arc set, and U denotes the capacities on the arc. So, U is a vector of capacities, right. And we say that if X is a feasible flow and W bar is a cut such that, so I am given a feasible flow and I am saying that I have a cut W bar such that if Xij is equal to Uij, then I belongs to W and J belongs to W bar, okay. And second condition, if Xij is 0, then I belongs to W bar and J belongs to W. Okay. So, that means when it is a backward arc in a sense with respect to the cut W bar, then the flow should be 0. If this, then X is the optimal flow or max flow, I should say, is the max flow and W bar is the min cut and X is the okay, here again the understanding should be clear. X is the flow, max flow vector, I should say, max flow vector, okay, because the components here denote the flow on the arc. So, the max flow vector, W is the min cut, and V bar is capacity of W bar, where V bar is the max flow. Okay. The idea, I just want to state the theorem because maybe it can be written in a better way, but anyway. So, then the value of the max flow will be equal to the capacity of the cut, and this will be the minimum cut, because remember the dual problem we were defining as the finding the minimum of sigma Uij Vij. So, this will be the minimum cut and this will be the max flow. Okay. So, proof is simple. Yeah, I have now rubbed out the this thing, but remember in your formulation of the max flow problem, the constraints were all equality except, see, you had Xij less than or equal to Uij. Yeah, these were the only inequality constraints. So, if you want to look at complementary slackness conditions, then this required that your Vij into Xij minus Uij should be 0 for all Ij, for all Ij belonging to A, right. So, this will be the corresponding to the primal constraints, this will be your complementary slackness conditions, because, so what means that if Xij is Uij, then your Vij is 0, or Vij can be anything, sorry, but when Xij is 0, then Vij must be 0. Okay, because when Xij is Uij, this is anyway 0, so it does not matter what Vij is, but when Xij is not equal to Uij, that means less than Uij, which means it is 0, then Vij must be 0, right. And this is what we are defining here. We are saying that, remember, for the dual solution, when you have a cut W bar, we are defining the dual feasible solution. Vij is 1 when I is in W and J is in W bar, and when it is the other way, then Vij is taken as 0. So, that was required for the dual feasibility. So, therefore, here actually one does not need the proof as such, in the sense that all we need to say is that from LPP theory we can verify that x and the corresponding dual and the dual feasible and the dual feasible solution corresponding to the cut W bar satisfy the complementary slackness conditions. Maybe I should also slackness conditions. Yeah, you have to do the work, because remember for the dual constraint I had pi I minus pi j plus Vij greater than or equal to ES. When I wrote the dual constraint, I forgot about the I didn't write. I'll do that immediately. I'll so make that correction. This is greater than or equal to 0, and I for the v for the variable v I did not write the dual constraint, which is minus pi s plus pi t, and this is because v is unrestricted, comes out to be 1. So this is anyway always satisfied, right, because we choose pi s to be 0 and pi t to be 1. So this will always be satisfied. So again, no problem. So but and this one would be pi I minus pi j plus Vij. So here the complementary slackness condition would be corresponding pi I minus pi j plus Vij into xij. This should be 0, right, for all ij, and that you can see from here that when you have I is here, and so in fact you would need to take all possible cases, as I discussed for dual feasibility when I was trying to prove that this is a dual feasible solution. Then you just see that here I'll take up one case that I is here, j is here, then your pi I is 0, pi j is 1, and this is also 1. So therefore this is 0. So then xij can be positive, which is happening because then xij is uij according to here, right. And now you can also discuss the other possible cases. So what I want to say is that if an x and a corresponding and a cut w bar satisfy these two conditions, then the complementary slackness conditions are satisfied, and therefore we immediately get that the two solutions will be optimal. That means x is the max flow and w bar will correspond to the min cut. Now you want to show the value of the, so and what will be the value of the cut, right. So therefore here, and yeah, we want to look at the, so therefore satisfy the complementary slackness conditions. Therefore x is the max flow vector, right, and w bar is the minimum capacity cut. Okay, this comes from our complementary slackness conditions, but you can otherwise also see, or otherwise alternatively you can also check. See, we said that the net flow across a cut is given by this, right. So alternatively net flow across w bar is equal to what? By this definition, by the because these conditions are being satisfied. So you see for I in w, j in w bar, xij is uij, right, and this is 0 when it's the other way. So here when you write down this, you see this flow is 0 because for k in s bar and I in s, the xkj's are all zeros. So therefore this is 0, and so you get that net flow across w bar is simply summation xij I belonging to S, j belonging to S bar, which is equal to summation uij, I belonging to S, j belonging to S bar, and that is equal to your flow by that equation. Right. So, alternatively also you can prove it, because you will find that some textbooks may not use linear programming theory to prove all these results, which is fine, but I feel that you have a good background of linear programming theory by now, and therefore you can also see that you can easily prove this result, right. So, this is equal to V bar, and so once because we said that the flow across any cut, the flow in a network will always be, remember the weak duality theorem, I already showed you that the flow in a network will always be less than or equal to the capacity of any cut. Now, once the flow is equal to the capacity of a cut, then they both must be optimal, right. So, we have shown that the maximum flow will always be equal to the minimum capacity of the capacity of the cut, which has minimum capacity, right. Okay. So, this almost gives you the theory behind the, and so this will be our stopping criteria also when we want to show that we have a flow. That means, so now when we develop an algorithm, our stopping criteria will be that the moment we have a flow which satisfies these conditions and we can determine the cut W bar. That means, if I given a flow, I can find out for you W bar such that these conditions are met, then I will stop, because I know that the flow must be max flow. Okay. Yeah, so now the idea is to develop an algorithm, okay, and this will be a very simple algorithm I will give you, and because the course does not really have it in its scope to give you, have a lengthy, because otherwise we might end up having 7 to 8 lectures on discussing the real state of art max flow algorithms. So, let me just give you an idea here. So, this will, I will be giving you the labeling algorithm. Labeling algorithm for max flow problem. Okay. So, the idea here is, see, let us look at the how, so if you have a node I and there is an arc like this j. So, we will give the label here, two labels, L1 and whatever the this thing L1I, okay, and then L2I. So, these will be the labels associated with any node. L1I will indicate, so this will be the node from which node I is reached. This is the node from which node I is reached from S. Remember, we want to, as I told you, the basic idea is to build up paths which have positive capacity, so that I can flow a certain amount on that path. So, this will indicate the node from which, somewhere here, from which I am reaching I, and then that node is reachable from S. So, therefore, essentially we start from S and I am finding the path. Now, if xij is less than uij, then I will label this as I, and this will be minimum of, and I will explain, L2I and uij minus xij. So, this will be minimum of this, and so this will be the label. So, as I said, because now you have an arc from I to j which has some capacity left on it, because the flow currently is less than uij, I can increase the flow on this arc. So, therefore, I will label the first label as I, same thing, because j is now reachable from S, I can come up to this point, and then the second label tells you the amount of flow that can be flown up to this point. So, L2I was the okay, so I should have said here L2I is the amount of flow that can be sent from S to I. So, let us just see, yeah, I was telling you how to label a node from a node which has already been labeled. So, the two labels, the first label indicates the node from which I is reachable from S. So, through that node you come to I, and then L to I is the amount of flow that can be sent from S to I, right. So, now when I want to label J, in case Xij is less than Uij, the first label will be node I, because J is reachable from I, and so the path that was coming from S to I can now come up to J, right. And then the amount here which can be sent from S to J obviously has to be the minimum of the amount that was already been, that can be sent to I, and then the amount which is can be sent on this arc. So, the minimum of the two. Remember, I defined for you the capacity of a path as the capacity of the minimum capacity of an arc on the path. So, therefore, here this number has to be minimum of the two, and then this will be the label, right. In case your arc is like this, so I has been labeled and this is J. So, then what here you will require that Xij should be greater than 0, because when you want to label J from I, that means you will be reducing the flow on arc Ji essentially. So, if there is a positive flow from J to I, when I traverse it in the opposite direction from I to J, I will be reducing the flow. So, here if this thing is L1 I, whatever it is, and this is L2 I, the label. So, here the label will become minus I. So, that indicates, see here I did not write plus I, it is understood, but minus I means that you are traversing the arc in the opposite direction. That means the arc is actually from J to I. So, I write minus I, and then this will be minimum of, again the same thing, I can reach this much flow up to this point from S. So, now here it will be minimum of Xji. Okay, I should have said here that Ji is positive, okay, because flow is actually from J to I. So, minimum of Xji and no, L to I. So, this is your label. So, once you have this method of labeling a node already labeled, so then we start looking for, so here let me give you the algorithm. So, this is Ford and Fulkerson's algorithm actually, Ford and Fulkerson's algorithm. So, we begin with, label for S as 0 m, where m is a very large number. See, we have no idea how much flow we will be able to send from S, so we will just leave it as 0 m. So, this is the thing. Then label all nodes, and initially where m is a very large number and 0 flow in the network. So, for that we have to say, and you can say that x is 0, and all labels, okay, all other labels are zeros, all other labels are 0, right. Then you start to, so, and you maintain a list, of labeled nodes. So, this is all your initialization. Start with all 0 labels except for node S, which has the label of 0 and m. Then currently the flow in the network is all 0. You have a list of labeled nodes. So, in the beginning right now, so S belongs to this to start off, right. then you idea is that you and now so you label all nodes from S by our method, right, and add them to list. So, and this is also called scan. It's easy, scan S, right. You scanning a node means that it's already labeled, it's in the list. You take it out from the list, and then you label all possible nodes from that node and add them to list. So this is what you call, right. This is called scan S. Then the second step will be, now pick a node I belonging to list and scan I, right. So repeat this process. When I scan I, again whatever nodes I can label from I will add them to list. So repeat this process till one of the two following things happen. Okay, right. See, remember the idea is to find an augmenting path. So if I label two following for one of the two following things happen, one is node T gets labeled. Node T gets labeled, right. This means an augmenting path has been found. An augmenting path has been found, and so augment the flow by amount L to T. Remember, the second number indicates the amount of flow that can be sent from S to T. So augment the flow by amount this thing, right. Update the flow. Acha, augment the flow, but so an augmenting path has been found, and how do you find the, so this is to find the path trace back from L1T. I'll just explain to you in a minute. See, that means because this node tells you, this label tells you how you reach T, and then when you go to that node, that will tell you how you reached there. And so as you go backwards, so find the path, so trace back from L1T, and you will find the path up to C. So you will find the augmenting path. Then on the augmenting path, you will augment the flow by amount L to T, and then update the flow. Update the flow, that means you will change these numbers, right, and update the flow and go back to the initial step, go back to the initial step by putting all labels to 0, all labels to 0. So all that work you did in the first iteration is not going to be used at all. You will need to start labeling the nodes again and again find a augmenting path. So let us look at, for example, here in this case, let us look at this example. You have this, and let's try to start labeling from node S, right. So I'll use it here because yeah. So suppose what is the label for S? So S is 0M. I'm starting with, right. Then if you look at node 1, this arc, this is not saturated. There is a flow of 1 unit available, right. So here the label would be S, and then the difference is because this is m. So, the minimum of m and 1 will be obviously 1, because m I am saying is a very large number. So, this is the label for node 1, right. Similarly, for node 2, the label again it is reachable, S2 is not saturated, there is a capacity of 3 units left on this arc, and so the label would be S and 3 again, because m is a large number, right. Then from 2 1 is already labeled, so you cannot label. So, let us look at 2 3 2 6. So, 2 3 is what? 2 3 is this one here, the capacity. Okay, I cannot label 3 from 2 because this is already saturated. Remember, for forward arcs the arc should not be saturated. So, I am not able to label this here, right. Then 2 6 you can label because it is not saturated, and this capacity leftover capacity is 2. So, therefore, this will be 2 and 2, right. Minimum of 3 and 2 will be 2. So, this is what. So, this is what, see, you are building up the path, and it tells you that starting from S you can come to 2, then from 2 you can go to 6, and the flow that can reach up to 6 from S is 2 units right now. Okay. And then if you like, you could have, see, that is what I am saying here, in the algorithm nothing is spelled out as to how you will operate the list. See, all it says is pick a node I from list, nothing is said about it, and therefore I could have, for example, chosen from here to label T, and the label T I cannot do it. Why? So, I'll stop here, and from 6 now if you can label 5, right. Okay, so let us do it. From 6 you can label 5, which would be, sorry, the arc is this way and flow is 2 here. This is the arc. I will label 5 here, but what will be the labels? See, remember it is backward, so it will be -2 and 2, because I can reduce the flow by 2 units. 2 units is here, and so the minimum of this and this number is 2, so I can do it this way, right. Now, from 5 I cannot label T, but I can label 4. So, which is again a backward arc. So, write it this way, 4, and here again the label would be -5, and the flow is 2 again. So, this will be 2, right, and then from 4 you could label T, and what would be the because there is no flow on 4T. So, therefore, the minimum of 2 and 3 is 2. So, this tells you that you can have 4 and 2. So, therefore, the augmenting path has been found, which is S2654T, and says that you can augment the flow by 2 units. And as I said, once you have labeled T, you can trace back the path, because this tells you came to node T from 4. 4 tells you that you came by 5 by a backward arc. So, you come here 5. Why did I write -2? This is -6. Okay, sorry. So, this is -6 because I came from 5. I came to 5 from 6 by a backward arc 6. Now, this one has a label 2, which says that you came to 6 by a 2, and 2 I of course came from S. So, this is how I trace the path. This number tells me the capacity of the path. So, I can augment the flow by 2 units, and so therefore, these numbers will go up, right. So, here this number will go up to 6, and this will go up to 4, and then this number becomes 0. This is there is no point writing circle here, because we are not talking of a basic feasible solution or anything. So, this, and then here this is 2. Okay. This is how I update my flow. Okay. So, all labels are erased. Now, I will start again, and let us see what will be my labeling scheme. So, here again S1 is the same thing, because that flow did not change. Then 2 can also get labeled again. So, this will be S and 1, right, as a unit flow. Then 2 3 I cannot label, sorry, 2 3, yeah, now I can label. Why did I not label? Acha, 1 is already labeled, fine. Now from 2 I cannot label 3 or 6, right. So I'll go look at one node 1 here. Now node 1, this is saturated, the only arc available is 1 3, so we will do this, and here the first label is 1 and the second label is 1, right, because this flow is 1 unit, and also what you can reach to 1 from S is 1 unit. So this is 1 1, right. Then from 3 you cannot, we could label, well, okay, that's it, you cannot go for any further, right, because from 1 to 3 I could just increase the flow by 1 unit. This was 4, so 1 unit was there, so that's right, I cannot do anything here, and that's it, because there is no backward arc for which I can reduce the flow. See, this is already labeled, node 2 is labeled, so I could go from here to here, but cannot do it, and in any case this is also saturated, right. So this is what you have, so that you have 8 and 2 10 units of flow, you have 10 units of flow, fine. So now what we will show you is that once the algorithm stops, that means the go back to the so I did not tell you how to find. So now we will come to, that means you go on augmenting. So this was an example to show you how you will find an augmenting path and then augment the flow. So then what would be the termination criteria? The algorithm stops, I'll just write the algorithm stops when node T cannot be labeled, right, and this is what I will prove to you. So let's quickly do it. See, here we could label 1 2 and 3. So therefore what I'm now going to show you is that my cut, this will define my cut, okay. So the nodes which get labeled, so when the Forden-Fulkerson algorithm stops and T is not labeled, so therefore all nodes which have been labeled, I'll call them as part of S, and the other nodes will be part of S bar. T obviously will be in S bar, S is always in S. So now you see that if you look at this cut, see the capacity of the cut is 4 4 and okay, this is 3. Oh, so that means there is something missing. So that means we will, because this is a good check, that means my algorithm should not stop here right now. I can label something more, because the capacity of the cut right now, currently the flow is 10 units, but that means I should be able to, why didn't somebody correct? So here, okay, we will look at the problem again, because my this thing is this, the cut is this, not this one. Yeah. So the cut is this. All the 3 arcs are saturated, 4 4 and 3. So the total flow should be 11 units. Maybe this one I did not write the number correctly. Well, okay, so we'll revisit the problem, because here this one is showing that the capacity of the cut is 11. If this is the cut, then I should be able to show that there's 11 units of flow in the network. That means we should be able to increase the flow by 1 more unit. Okay, so we will see. We will correct the calculations needs to be checked. This arc was missing in the network. That's why you see, whenever you start with a problem, always make sure that the flow conservation equations are satisfied. And so therefore, for arc 4 3 is there, and then see the 3 units of flow was coming from here. Only 2 was going out here, so 1 was going here. This was needed, right? So once this is there, you see, then I can label 4 from 3, right? Okay, so this stopping algorithm criteria was given, and so from 3 you can label 4, and this will be minus 3 and 1, right, because you have flow of 4 3, so this will be this, and so again you can find an augmenting path which would be 3. So this will be the of course right now the label would be 4 and 1. Okay, so once again you have labeled T, and the augmenting path is you are coming here from 4 to this is this. So, therefore, this is backward -3, then you are coming to from here 1, and from 1 you are coming from S. So, this is another augmenting path, and so your total flow will go up to now 11 units, and therefore, see after this you will see that we will continue with now you try to find out once you augment the flow that the cut will be that you when you cannot anymore label the nodes, when the labeled nodes you will form as S and the others as S bar, and they will form the cut for which the capacity will be equal to the flow in the network. Okay.